Hi, it's Chris Good here. This is a solution to repeated measures ANOVA practice problem number 3. So here, subjects are given 3 treatments to try to help with their kleptomania, and then they measure the number of objects that they steal. So I've copied these data into this Excel sheet. We'll do a repeated measures ANOVA. And that means that we need to do all of the same steps that we've done in the other 2 practice problems. So let's see what they are. We've got to state our null hypothesis. That's that mean 1 is equal to mean for treatment 2, which is equal to the mean in the population for treatment 3. And then at alpha 0.05, we're going to need to evaluate F crit on what degrees of freedom? Well, in order to do those, we've got to start filling in our source table. So K is going to be the number of treatment means that we have. So let's do those first. Average for treatment 1, treatment 2, and treatment 3. K is the number count of means that you have, right? We'll need big N, that's the number of scores that you have, right? Notice I'm not counting the subject numbers. That's not a score. Those are just numbers for subjects. And that is all we really need for between and within treatments degrees of freedom, but I am going to need a count of scores within each condition. It's equals count for or between subjects. I only need one of them, but I'm going to do it for all 3 groups because I need it later when we do our t squared over little n. So let's move this down here and do degrees of freedom between treatments. Degrees of freedom between treatments is K minus 1. Within treatments is big N minus K. And between subjects is little n minus 1. So we can get error degrees of freedom by subtracting within subjects minus between subjects, and that's 6. So this F crit is going to be for 2 and 6 degrees of freedom. And we'll go to the F table to see what that is. For 2 and 6 degrees of freedom, F crit is 3.46. And let's see how close to that we can get when we calculate F. Let's do between treatments. Actually, you know what? Let's do this. Let's fill in total degrees of freedom. We know that that is between treatments plus within treatments. And the same thing is true for sums of squares. We're going to get within treatments sum of squares by subtraction. Let's start with between treatments sum of squares, though. We need our t's, which is the sum of your scores within each treatment. We'll square those. That's t squared. And then we'll divide that square by little n for all those groups. And now we've got everything that we need. Oops. No. Let's do this. T squared over n is equal to t squared over n equals t squared over n. Copy that, paste that. There we go. We'll need g, which is the sum of all the scores. And we'll need g squared. And we'll need g squared over, that's not little n, it should be big N. Let's change that. G squared over big N. Okay, now we've got everything we need to do sum of squares between treatments, which is sum of these t squared over little n's. Ooh, not that one. This one. T squared over little n minus, not divided by, minus g squared over big N. Okay, that's between treatment sum of squares. To do total sum of squares, that's the total of the squared deviations of every score from the mean of all the scores. So let's get the grand mean, the mean of all the scores, as the average. Average of all the scores. There we go. Now we can get deviations for each treatment score. So it's this minus the grand mean. But we want to make sure we're always referencing the same grand mean for every one of these scores. And then we're going to square those deviations. So that one's this deviation squared. And then we copy and paste that formula to get all of the squared deviations from the mean. And that's total sums of squares. Total sum of squares is the sum of the squared deviations of every score from the grand mean. Now we can get within treatments sum of squares by subtraction, which is total minus between treatments. Great. Now we need between subjects sum of squares, so we'll need our p's. So it's kind of like doing between treatments, except it's between subjects, where you get p's, which are kind of like t's for treatment conditions, right? And then p squared is just squaring it. And then p squared minus k is p squared minus k, but I want to make sure it's the same k for every participant, each one of our 4 participants. And now we can get between subjects, which is the sum of p squared over k minus our friend g squared over big N. Now we can get error by subtraction because, I made an error. And how do I know I've made an error here? It's because between subjects has to be smaller than within treatments. So let's go back and see what happened here. All right. I know what I did. I subtracted the grand mean instead of g squared over big N. Let's make sure I didn't do that here. Okay, that's right. Did I do that here? No, I did that right. Let's do this again. Between subjects is the sum of p squared over k. That's what's wrong. Those can't be p squared over k's. I subtracted k instead of dividing. Yep, trying to go a little too fast. There we go. That's where the error was. So now I can sum my p squared over k's minus g squared over big N. That's much better. Now I can get the error by subtracting within treatments minus between subjects. You subtract subjects from treatments to get error. And now we can get the mean squares that we want. Sum of squares over degrees of freedom. Same for that. And f then is mean square between treatments divided by mean square error. Ooh, that's small. You know what? We calculate our f. I think we're going to fail to reject. Well, that means we only have to write one sentence. So it appears that there's no significant effect of treatment on the number of items stolen with f at 2 and 6. Degrees of freedom equal to 0.33. And p less than 0.05. No, it's not less than, it's greater than 0.05 because we failed to reject. And we're done. We will see you next time.